Okay, today we are going to start on module 5, which is basically it's about traffic flow theory and shockwave analysis. First we are going to start with car following model, then the macroscopic flow model, then shockwaves application. So we start here. Okay. We start here with car following models. Okay. So what are car following models and why we need it? Car following theories and models dictates the distance between vehicles and the estimation of traffic density in the traffic stream. So why we need the car following models? Car following models we usually need it to better model the behavior of drivers on the street. That's number one. Number two, now with the new emerging of autonomous vehicles, okay, these vehicles needs a following following model that controls its logic in driving on the streets. So that's another key application for car following models is in simulation modeling. You know, have you ever wondered how does the vehicles move on PTV VSIM? It moves from one time increment to another time increment using a car following model. So that's basically to give you a background about the car following models. So the distance, before we go into depth, what are the key parameters in the car following? We have what we call distance headway. Okay, what is the distance headway? Distance headway is basically the distance defined as the distance from the selected point on the lead vehicle to the point on the following vehicle. That means if we have two cars, so from the front bumper to the rear bumper, that's the distance headway, which is here, dn+1 t. That means the distance headway for vehicle n+1, that's the following car or the following vehicle, equal the length of the front vehicle plus the distance gap, okay, between or the gap length between the two vehicles, as you can see here in this figure. So that's the g, and that's the length of the leading vehicle. So the distance gap is defined as the gap length between the rear edge of the lead vehicle and the front edge of the following vehicle. Okay. We start first with time headway. Time headway, okay, it's better than distance headway in terms of it's easier to measure. Okay, distance headway can be obtained from maybe photography or from aerial photography, but usually we obtain the distance headway from the time headway, as you can see in this formula. The distance headway for a following vehicle n+1 equal the time headway, this is the time headway, multiply with the speed of the following vehicle. Traffic density, then, if we have the distance headway, then the traffic density is simply 1000 by d. d bar, that's the average density headway in meters per vehicle. And so the units here will be vehicle per kilometer per lane. That's how we calculate the density. Okay. Car following theories. Let's have some background about it. The theories describing car following behavior started as early as in 1950s and 1960s. Pipes was one of the main contributors to this, and Forbes in the early 50s and 60s. Then in the 1960s, there was 3 parallel efforts by a group in Japan led by Komatani Sasaki, and Forbes in Michigan State University, and General Motors Research and Development Team. These were the 3 core contributors for the development and the evolvement of the current car following models. Before we start, we need just to have some notations that we agree upon. So we have the lead vehicle, we will refer to it as vehicle N. The following vehicle will be N plus 1. The speed of the lead vehicle will be xn dot at time t. The speed of the following vehicle will be xn plus 1 at time t dot. The length of the lead vehicle ln, the length of the following vehicle ln plus 1. The position from a reference here for the lead vehicle is xnt. The position for the following vehicle is xn plus 1 at time t. The acceleration for the following vehicle after time t, at time t plus reaction time, it's x double dot n plus 1. So these are the fundamental values or the fundamental notations that we will be using from now on in this topic. Any question? Okay, let's start with Biebs. Biebs theory, it was based on the following concept, that there should be a safe distance. Drivers, when they drive their cars or vehicles on the road, they try to maintain a safe distance. From his perspective and from data that he collected, okay, this safe distance was to allow the driver at least a length and a length of a car between his vehicle and the lead vehicle, and for every 10 miles per hour, you leave a space for a length of a vehicle. That means that's the speed divided by 10 miles per hour, and this is conversion factor from miles per hour to feet per second. So you multiply it with ln. Ln, that's the length of the lead vehicle, plus the lead vehicle length. So that was his, D minimum. That's the minimum safe distance headway. Okay? If we consider a vehicle length of 20 feet, okay, then we end up with this simplified form. If we plot, okay, of course, the headway, the minimum headway according to this, headway minimum at time t equal this value divided by the speed of the following vehicle. So it's 1.36 plus 20 divided by xn plus 1 at time t dot, which we find it here. Biebs plotted his values that he got from his model and compared it with field results. There was a data set that he had observed, several drivers at different time, at different speeds, and he measured their minimum safe distance headway and their minimum safe time headway. And the gray area, that's the field results. The solid line, that's the value that you get from Biebs theory. As you can see here in this region, at high speed, Biebs theory gave us a lower, okay, minimum safe headway. That means that is the safe headway, and Biebs, said that's the safe headway, which means this is risk. And here at lower speeds, he said that, leaving this headway is safe, but the observed headway was higher. Also, the time headway, the solid line here at low speeds, okay, say for example here it was 2.5 seconds, but in reality it was almost 3. So at lower speeds there is deficiency, as you can see, okay, but that was a pioneering work at the time, and he was, major contributor to the state of the art. So Forbes later on linked the time headway with the reaction time needed of the following vehicle. So he mentioned that okay, the time gap between the rear of the vehicle and the front of the, the rear, the time gap between, that's the lead vehicle and that's the following vehicle. And he said that the time gap between in this area, okay, should always be equal to or greater than the reaction time. That means if we say this is Ln, that's the length of the lead vehicle, then this should be greater than or equal delta T, which is basically the reaction time. Tamam? So that means the minimum headway, which is here, that's H minimum, should equal delta T plus the length of the lead vehicle divided by the speed of the lead vehicle. Okay? Okay. From that we can calculate, if we assume that the reaction time is 1.5 seconds and we have a vehicle length of 20, we will end up with these values. If we compare it with the field results, the same data set that Pipes had, you can see that Forbes kind of improved at high speed, okay, but still there is some great discrepancy here at low speeds. Okay, then there was the work that was done by General Motors, GM, and their researcher came up with with 5 models. These 5 models was based on this relationship, that the response of the following vehicle is function of sensitivity and stimuli. What do we mean with the response? Response was always represented by the acceleration or deceleration of the following vehicle. In other words, the following car, it is going to accelerate or decelerate. That's the response. So this response depends on what? It's function of stimuli, okay, the thing that cause the following car to increase speed or reduce speed, to accelerate or decelerate, plus the sensitivity of the following car. So here, the stimuli was always represented as the relative velocity of the lead vehicle. That means that's the difference between x dot, between the two vehicles, n minus x dot n plus 1. The difference in the speeds, that was basically the stimuli. However, when it comes to the sensitivity, that was the key difference between the 5 models that was generated. As we can see, as we will see now, each model started evolving, and the sensitivity term started changing and evolving with each model of the General Motors family models. We can see here, for example, that's the initial model. That's the first model. They say that the acceleration of the following vehicle at time t plus reaction time equals alpha, which is sensitivity factor, multiplied by the difference in the speed, which is, this is the stimuli, and this is the sensitivity. Okay? Based on field results, they found that the minimum reaction time was 1 second, the maximum was 2.2, and the sensitivity was between 0.17 and 0.74. Okay? So now they, proceeded with this model, and they came up with this second model. And they said we have either alpha 1 or alpha 2, because it's 0.17. So, and it's up to the user to change. This model was problematic, and it was difficult to implement, because on what basis should I select alpha 1 or alpha 2? And it's kind of judgmental between different users. So that led to the development of the third model. But before we go to the third model, they found out that the relationship between the sensitivity and the spacing between the vehicles was like this fact. That means when the vehicles were the 1 over d was, that means at 1 over d, that low value, that means they are far apart from each other. You see, the sensitivity was low. But when cars got closer to each other, the sensitivity started increasing. That means alpha is proportional, okay, or sensitivity proportional to what? To 1 over d. Okay, as this term increase, sensitivity increase, and this increased when d, the spacing between the vehicles, decrease. Okay, so they came up with this form: alpha node divided by the spacing between the front vehicle and the between the lead vehicle and the following vehicle. Okay, and they started calibrating this model. Okay, and they did some testing at General Motors test track, and they got the delta T was 1.5. The alpha node was 40.3 feet per second. They did the same measurements at Holland Tunnel, okay, that's in New York, and Lincoln Tunnel, okay, and these were the values that they got. Actually, this model is a key breakthrough, because from this model there's a direct link to Greenberg macroscopic model, as we will show later today, inshallah. Then they developed, okay, that was the third model. There was the fourth model, which I don't have it here. Okay, so they came up with the fifth model here, which is basically a function of, it has parameters. First is multiplied with the speed added to the sensitivity term, the speed of the following vehicle, okay, and meant, added a power here, L and M. So that's kind of a general model. So if you substitute for M and L with 0, you come up with the first and second models. If you give L a value of 1, then you end up with the third model. If you give here 1 and 1, then that's the fourth model, basically. So that's the fifth and fourth model. The fourth model is basically M equal 1 and L equal 1. And at this point, alpha is unitless, because we have speed divided by spacing multiplied by speed. It will give you acceleration. Any questions so far? Okay, we're going to take a break for 5 minutes, but before we go to break, hold on for a second. Okay, so far we have discussed the car following model. These are macroscopic properties for the traffic flow. Then we go into the flow or traffic flow models macroscopically. So first we start here with the speed density model. So we had a green shield model, which assumed that there's a linear relationship between speed and density. All what we agree on, when there is no vehicles on the road, all vehicles will be driving at very high speed, at the free flow speed. But when there's a jam density, okay, no vehicles will be moving. All the speeds will be 0. However, different models, they varied with what's the relation between the free flow and the jam condition. So in green shield model, he started with a linear simplistic model like what we see here. Greenberg, okay, it started with a different model, with a natural logarithm model like this one. Underwood developed this model, which is basically that the speed is free flow speed multiplied with the exponent of k over k jam, like this one. However, as we will demonstrate now, that there is a link between Greenberg model and the models that was developed by General Motors research and development team. We will show now how we can derive from GM models, okay, the Greenberg model. So here, let me just share this with you. Basically, the GM model 3, what it says that the acceleration of the vehicle n+1 at time t plus delta t equals to alpha node divided by the spacing between the lead vehicle, which is xn at time t minus xn plus 1 at time t multiplied by the difference in the speeds, which is basically xn at time t dot minus xn plus 1 at time t dot. So now, in order to if we do an integrate with respect to time t, if we integrate this equation, what we will get? We will get x dot, okay, n plus 1 equal, what's the integral of this? Alpha node over, if we can put this as a u, we can put this as a du, right? So here we will have alpha node multiply len for this value, the natural logarithm for xn, okay, we are not going to write the t, but we know it's 40 xn, I'm sorry, this is minus xn plus 1 plus the constant of integration. So now that's now the speed of the following vehicle equal alpha node len xn minus xn plus 1 plus c. So if we just replace, replace or substitute, if we substitute xn plus 1 dot with v speed, okay, then, and also if we replace xn minus xn plus 1, xn minus xn plus 1, this is basically the distance between two vehicles, right? Distance headway, correct? That's xn minus xn plus 1. If we say 1 over d, this equal the density, correct? So if we replace this with 1 over k, density, So this formula will become now V equal alpha naught natural log of 1 over K plus C. Now, if we replace C, if we substitute C with alpha naught len C dash, what we get? This formula becomes V equal alpha naught len 1 over K plus alpha naught len C dash. In other words, we will have V equal alpha naught len C dash over K. Correct? Good. Now we want to find the value of C dash. Let's check the boundary conditions for this relationship. The boundary condition says that that's the speed V and that's the density K. So the boundary conditions say at speed, here the speed is what? V equals 0, K equal K jam. And here V equal VF and K equal 0. Correct? يبقى at V equal 0, K equal K jam. So let's substitute with this boundary condition. We have V equal alpha naught len C dash over K jam. From here we can say that C dash equal K jam. Then we end up with V equal alpha naught len K jam over K. Now we need to find out what is alpha naught. Let's go to the flow condition. The flow condition say that it's kind of a parabola like this, and that's density, and that's flow. Q. Q equal V multiply K, correct? And at the maximum here, the slope Q dash equals 0. Remember this. And the density here is K optimum, and the speed is V optimum. So if we develop a Q equal K multiply V, K multiply V, that means it's K alpha naught len K jam over K. If we differentiate dq over dk, we will end up with the following. Now you can see that there is a multiplication here, so we need to solve it in steps. So the differentiation will result in the following. First, we differentiate the first part. We have k, so this is the differentiation will be alpha naught multiply len K jam divided by K. That's easy. The second term, which is basically the differentiating this. So this will be plus alpha naught K. Now we are working at K optimum. So this is going to be K optimum also. So this is K optimum. And here, this will be K. We're going to differentiate this one. So it's, the K jam over K will be inverse. So this is going to be K optimum over K jam minus K jam over K optimum square. Okay, so this will conclude down to len K jam over K optimum equals 1. Okay, because if you, this is multiplied here, so if you multiply this, this will cancel with this will cancel with this, okay, and this should equal to 0. So we will end up with I'm sorry, let me just erase. This will end up simplified to K jam by K optimum minus 1 equals 0. So here we have length K jam over K optimum equal 1. That means K jam equal K optimum multiply with E. Okay, or in other words, K jam over K optimum equal E. Okay, and K jam equal or K optimum equal K jam over E. So at U, the speed in this case at K optimum will be, yet at K optimum, the speed V optimum equal alpha node multiply the natural log, okay, of K jam divided by K optimum. Then we're going to substitute here with alpha node len K jam divided by E over, K jam over E. So this will end up, this will cancel together and E will go up. So we have alpha node len natural log for E, which is 1. So this will be alpha node. So based on this, we can say the speed model that we can get, it's V equal V optimum len K jam over K, which is basically Greenberg model. And we were able to derive it from the microscopic model by General Motors. Clear يا شباب? So that's actually the strength that we can demonstrate in this model, that it links between the macroscopic, and you can link it from the macroscopic to the microscopic level. Any questions so far? So basically, the C here is the speed at maximum Q rate or maximum flow rate, which is V optimum. Okay. However, maybe we shall use this model more frequently than this model, because this one is easier to handle and to deal with. But in more sophisticated applications and in simulation models, okay, sometimes they use, you know, something like that. Any questions so far? Okay. Again, here the flow is basically function of the speed multiplied by the density. So that's Q. The speed, as we mentioned, it can be either linear minus K over K jam, or that's the green shield model that we have here, or like in Greenberg model, V could be V optimum len K jam over K, or like in Underwood, exponential, like here. Clear? So that's the flow density diagram, as we mentioned, and that's the speed flow diagram, which is basically the division of the discharge rate over the density, as you can see from here. So now we will shift gears toward the shock wave analysis. So what do we mean with shock wave? Shock waves are basically a boundary between two states of the flow. That's the shock wave. And the speed of transmission of transition between these two states, that's what we call the speed of the wave. Okay? So basically, flow speed density states change over space and time. When these changes of state occur in a boundary, a boundary is established that demarks the time space. Okay, to give you a better example for this, look at traffic signal. This is a space-time diagram, as you can see, and we have here 4 waves, as you can see. First of all, there is the stopping wave. Vehicles arrive and stop, then arrive and stop. As you can see, there is a wave of stopping vehicles growing backward. This is what we call backward forming. And we have 2 different states. We have state A and we have state B. If we plot the flow density diagram like this, say for example we are here in this state A. State B will be somewhere here. Okay? And this line is basically progressing in this way. Actually, if you draw this to scale, these 2 lines should be parallel to each other. Okay? That's good. Then, once the signal turns green, vehicle starts moving. So you see there is a moving wave backward. This is basically changing the state from being stopping to discharging at saturation flow rate. So this state is the maximum flow rate. That's the saturation flow rate. Okay, and that's another wave here. That's a state C.
معلش دكتور.
Yes.
دكتور ايش نقصد بالهذه shock wave analysis؟
Yes. shock wave analysis او الويفز اللي احنا بنتكلم عليها، الشوك ويفز دي بتعرف حالات مختلفة من حالات السير. تمام؟ يعني لما السيارات تكون كلها بتقف، دي حالة وقوف، صح؟ والسيارات بتمشي حالة مشي. الخط اللي يفصل ما بين الاثنين ده اللي بنسميه الشوك ويف. تمام؟ هدي لك مثال اوضح. لو في عندنا كيو واقفه، في كيو في اشاره، اوكي؟
ممتاز.
When the signal turns green, the vehicle in the 10th vehicle, is it gonna move?
Yes.
لا.
No, it's not gonna move right away. Okay? It will keep standing until, okay, the vehicles ahead of it moves, or until the change of state arrives to it, or until the shock wave arrives to it. فاهمة؟
لا والله يا دكتور ما وصلت.
Let me just draw it to you like this. This is a queue of vehicle. دي كلها مجموعة من السيارات ورا بعض. اوكي؟ لما الإشارة بتتحول إلى جرين، إيه اللي بيحدث؟ أول سيارة بتتحرك. بعد فترة زمنية اللي بعديها بتتحرك، بعدها كده. يبقى زي ما تلاحظ في موجة الحركة دي. موجة الحركة دي بتبتدي إيه؟ تمشي في طابور السيارات ده. تمام؟ موجة الحركة دي هي الشوك ويف.
اها.
اللي هي بتعرف الفرق ما بين حالة الوقوف وحالة الحركة.
الفرق بين حالة الوقوف عن حالة الحركة.
بالظبط. نفس الشيء في الأرايفل عند الإشارة. لو أنت وقفت كده هتلاحظ إن إيه بعد شوية يبقى في هنا موجة من السيارات اللي بتقف. واضح؟
واضح واضح.
جميل. هنا let me just elaborate on this. This we call it backward forming because it's forming a queue. تمام؟ Here backward
ممتاز.
recovery. This one, okay, when the signal turns green, it's a backward recovery. فهمت قصدي ايه؟ بيحصل ارتجاع لحالة الحركة تاني. تمام؟ We are recovering from the queue. واضح؟
واضح واضح.
Okay. Is it clear for everybody?
Clear.
Okay. So these are the basic principles of queue. There are different types of queue. We have frontal stationary. Okay. We have backward forming, like we mentioned when the signal turns green. And we have forward recovery or moving. We have rear stationary. We have backward recovery and forward forming. We demonstrated some of these waves, and you can see we have here front stationary. There is a front stationary. The flow here is 0 and the density is 0. And the flow here is 0 and the density is jam density. And we have a wave here that is stationary. It's not moving. Okay? That's another example. If we have a road or a highway and there's a truck that, you know, joined the highway, okay, and get onto the highway like this, okay, then it comes out. But because the truck is slower than the speed of the stream, okay, starts, you know, vehicle starts slowing down. So the first vehicle arrived to the truck, it starts slowing down and following the same speed of the truck. Okay, then the vehicle after arrives slowing down. So it forms a wave. This wave is progressive or going forward. We call it forward and forming because there's build up of cars behind this truck. Okay, once the truck exit the freeway, then all drivers again go back to state C and they try to, you know, recover. So this one is backward recovery, as you can see here. And this one is frontal moving because it defined two states, two different states. No flow state. Here there's flow and congested. واضح? Any question? Okay. Shockwave equations. Okay, consider an uninterrupted segment of roadway, okay, for which a flow density relationship is known. Okay, how can we determine the speed of the shock wave? How can we calculate it? So it says that consider that we have two states, okay, uninterrupted segment, and we have like this one. We have state B and state A. So the traffic is going to change from state B to state A. This is a little bit congested. This is, you know, the traffic volume is lower, and we have this relationship. That's state B and that's state A. So there is going to be a wave, and it is going to be progressing this way. How can we tell that? Basically, the speed of this wave can be determined using these equations. Basically, the omega AB equal the change in the flow divided by the change of the density. As you can see, the flow here and density are different from the flow and density over here. Okay? That's how we calculate the speed of this wave. If it's negative, that means it's backward. If it's positive, that means it's forward. Clear? Any questions so far? Let's have this example, okay? Use the flow density diagram and combinations of the four flow states A, B, C, D in the shown figure to draw distance time diagrams showing shock wave and vehicular trajectories that result in the following type of shock waves. A, frontal stationary, okay? B, backward forming. C, forward recovering. D, rear stationary, backward recovery, and forward forming. Then repeat the problem with numerical solutions. Assume that the flow density diagram is based on a linear Greenshields model, where U, that's the speed, equal 80 minus 0.75 multiply K. Okay, the flows for states A and B vehicles are per hour. Hold a second. Here it says that the flow states A, B, C, and D are 1440, 960, 960, and 600 vehicles per hour per lane, respectively. Okay, so that's let's try to solve this problem. Okay, let's start with the following. We have I'm sorry, here we have this is the speed density relationship. As you can see, it's linear. Okay, so let's just calculate the omega BA. For example, omega BA equal delta Q divided by delta K. That means it's QB minus QA divided by KB minus KA. Now, this is QA, QB, QC, QD. Do we have anything regarding KB or KA? No. So let's now just do some we assume that we have linear relationship. In the problem it says that you use Greenshield model, so that's Greenshield model, and that's the equation of speed. So let's estimate UF. UF equal U at K equal 0. So that's the free flow speed. So equal 80 kilometers per hour. Okay. Now we want to estimate jam density. Jam density, how much? Okay, at K equal K jam, U equal 0, correct? So we have 0 equal 80 minus 0.75 K jam. That means K jam equal 80 divided by 0.75. So this will be 80 divided by 0.75. So that's almost 106.7 vehicles.
دكتور احنا قاعدين نشوف سلايدات يا دكتور.
Really?
يس
وانت
دكتور.
لسه مفتكرين بس دلوقتي؟
لا يا دكتور نحسبك تاخذ الارقام او القوانين.
لا. Here what we are saying is basically that's the states that we have A, B, C, D, okay, and that's the speed equation. That's a Greenberg model, a green shield model, I'm sorry. And these are the flows, okay, for QA, QB, QC, QD. And now we want to estimate the speed, the shockwave speed for omega BA. Omega BA is basically delta Q over delta K. Delta Q over delta K, that means the flow of in B minus QA divided by the density at B minus density at A. So we have QB and QA, but what about KB and KA? We don't have both. So let's go and try to make some calculations here. We said that the speed density relationship is linear according to green shield model. So at free flow, what is the free flow speed? We want to determine that. So it's 80 kilometers per hour. What's the jam density? At jam density at this point, the speed is equal 0. At jam density, K equal K jam, speed is equal 0. So we substitute here, so the K jam equal 106.7. Clear? Okay. Now we want to estimate B and A. Let's go now to QA equal VA multiply KA. Speed multiply density. So what's VA? VA is basically, here we will have, V equal 80 multiply 1, okay, okay. V is how much? 80 minus 0.75 multiply K A, and this is multiply KA. I'm sorry, KA. And this should equal to the flow at QA, which 1440. 1440. So we will end up with, let's just multiply these values together. We will have minus 0.75 KA square plus 80 KA. Let's move this to the other side here. So it's minus 1440 equals 0. Let's multiply it by minus 1. Can someone solve this for us, please?
83.73.
83.73 and
وهذا x1 وx2 is 22.92.
22.92. Okay, we'll go with this value and I will explain to you why. Okay, first of all, that's the jam density. So that's the jam density here, 106. And from this relationship, we can see that the state of A is on this side. So that means the density, okay, usually this value is basically K jam over 2. Okay, so this value here, that's the KA, this value. If for the same flow we were here, then this is going to be the value. Clear?
No, again دكتور بالعربي لو سمحت.
اوكي. دلوقتي في عندنا two values لنفس الدنسيتي، لنفس الفلو ريت. يعني عند الفلو ريت ده we have two densities. We have uncongested and we have congested. يعني ركز معايا هنا كده. ده الفلو ريت وده الدنسيتي. صح؟
صحيح.
الجنب ده بنسميه congested، الجنب ده بيكون نسميه ايه؟ uncongested. uncongested.
uncongested.
Okay, so
ممتاز.
here this is K jam. عند النقطة دي بيكون K بتساوي أو K
over 2
equal K jam over 2. correct؟ جميل. K jam احنا حسبناها كام؟ 106.7.
440.
لا، الفلو هو ال
الفلو معلش، الفلو
1440.
هو 1440.
لاحظ عند الفلو ده نفسه 1440 we have two states. في عندنا حالتين، يا اما بيكون uncongested او congested.
صحيح.
تمام. لاحظ ان في عندنا هنا K1 وهنا K2. واضح؟ K1
واضح.
اللي هي في الحالة بتاعتنا دي، و K2 اللي هي دي. وصلت؟
وصلت.
تمام.
دائما انا افضل اني اخذ شو اسمه الكونجستد.
لا مش تفضل،
الانكونجستد.
مش تفضل. And I will tell you how. Let's now check on the speed. VA, okay, VA in this case will be how much? 22.92 multiply, I'm sorry, we have 80 minus 0.75 multiply 22.92. هتساوي
62.81.
62
Yes.
kilometers per hour. Okay, let's try to see what's the speed in this case.
17.25.
Okay,
17.20,
kilometers per hour.
Yes.
Okay, so that means the slope of the line is going here. Okay, and we can see here from the figure it's below, it's in the uncongested region, correct? So we go with this value. The same, we will do the same for the KB, calculating the density in state B. So we have 80 QB equal VB multiply KB. So this will equal 80 minus 0.75 multiply KB multiply KB equal, what was the flow rate? $960. $960. If we do the multiplication, we have 0.75 kb square minus 80 kb minus plus 960 equals 0. So here we will end up with kb equal
minus 13.78.
كم?
Minus 13.78.
I think you have something wrong.
Oh, sorry. Okay. Minus 80. Yes, doctor.
No, there is no minus in it.
I mean 0.75 and then minus 80. Yes.
Yes, 0.75 minus 80.
Yeah, minus 80.
Yes, plus 960.
960. Yeah, 92.88.
92.88. This is
And
vehicle per kilometer per lane. And the second value?
And 13.78.
13.78.
78.
This is vehicle per kilometer per lane. Now, let me ask you a question, Abdullah.
Yes.
Which value shall we take?
Again, between the two numbers, the 13 and the 19.
Yes, here is B. Which value shall we take?
13.
13, because we are in the uncongested region, correct?
Yes, yes.
Excellent. So that's the value we want to take. Okay, so now let's go and back to our shockwave estimation. We want to calculate the omega BA equal delta Q 960 minus 1440 divided by, what is the density that we calculated? It was 13.78. So here that's the density at B, 13.78 minus the density at A, which is 22.92 equal, or omega B A equal
52.51. 52.
Hold a second.
No problem.
Okay, so it's plus 52.51. And what are the units? Kilometer per hour. It's speed. Okay? It's speed. Clear? So what does this mean? This means that in this situation, there is a shock wave going in that direction at that speed, 52.51 kilometers per hour. Okay? There is a change of speed. There is a change of density. Okay? And it's going this fast. Okay? And actually, just to give you a hint on how to determine that this is correct or not, as far as we are going up like this, it's going to be positive. If the shock wave is going this way, it's going to be negative and backward. For example, it changed from state A to state C. This is going to be backward shock wave. Let's just calculate this at state C, and we are going to stop that. QC equals VC multiply KC. So here we have 80 minus 0.75 KC multiply KC equal 960. Okay, can you tell me what is going to be KC in this situation? It's going to be this value.
0.75 KC.
You don't have to calculate it. You don't have. You have calculated it earlier.
Okay. Okay. Again.
But this. You know, in other words, let me just explain it to you. As you can see, B and C, they are on the same line. They have the same flow, but this one is in uncongested case and this one in the congested case. So that's the other root for the equation, which was 98 point, how much? Yes, you are right. It's 92. So it's 92.92 vehicle per kilometer per lane. So the omega AC equals delta Q over delta K. So here we have, let's check on the Q. We have how much? 14. Okay, let's Q A minus QC divided by KA minus KC. So here we have 1440 minus 960 divided by, what is the density at A? We calculated. It was 22.92 minus 92.92. This will be 480 divided by minus how much?
Yeah, the total will be
70.
the solution.
So it's minus.
The solution
minus
6.85.
How much?
Minus 6.86.
Minus 6.86, and it's kilometers per hour speed.
Per hour.
Okay, and as you can see, it's going down. Okay, clear يا شباب؟
دكتور الكي حق الاي ما تتغير صح في عندي في هذه الحاله لان موقعها واحد اصلا ما تغير من الاساس.
Yes, bravo. It's the density at A doesn't change because that's a state. دي حالة معينة. Okay, بس. Any questions so far?
ان شاء الله انها كويسه واضحه ان شاء الله.
إن شاء الله. طيب, we are gonna stop right here and we will continue إن شاء الله tomorrow. Okay? Okay, thank you all.
دكتور.
Yes.
ابغى اتكلم معك شوي.